I'm Reed Weber from the FRL Space Vehicles Directorate, Kirtland, New Mexico. I'm a research physicist, hoping to share with you this morning 2 examples of signals processing research related to very small signals in image data. So, for the last several years, the main concern for my research has been quantitative image analysis from space remote sensing systems. The primary obstacle here is that we're actually moving into what is essentially a communications bandwidth limited domain. So we're not able to get down all the data that we would like from a satellite on orbit to the ground to give us the most useful data products. I'm going to talk in just a minute about addressing that specific problem. In general, however, looking at future systems, we're really concerned with developing both new exploitation algorithms to make use of these new sources of data, as well as compression algorithms. The first example here is really a way to get more out of space ISR assets using data compression. Okay, so specifically what I'm going to talk about is a technique where we're approaching the problem by co-design of both a sensor and then the algorithms that operate with that sensor. So what that looks like practically is shown left to right here. So we can take a sample IR image, inject a synthetic signal, and send that through a sensor simulation model. So we're able to tune the sensor parameters itself and then see what the data looks like. We'll take that set of images, run it through compression decompression, which is modeling what happens as we send the data from on orbit to the ground. And then you see there that second set of images is actually the degraded image stack that arises from a lossy compression algorithm. After that, we'll run our analysis and detection routines and create a detection image from which we measure the detection signal-to-noise ratio. So what I've shown here is actually what happens. That bottom right plot shows you as we vary the compression ratio for a variety of algorithms, how that affects our ability to detect the target that we've injected in the scene. Yeah, overall what we see is this is for a very difficult to detect signal where we see that kind of 3 times performance increase compared to COTS. If we go to an easier case, a stronger signal, we actually can outperform COTS by several hundreds of times. That allows you to go to much faster frame rates and even much larger areas of interest on your focal plane array in space. Second application I'd like to talk about is actually an extension of these kind of techniques that I just talked about to the air domain, where we're looking at characterizing jet engine plume signatures. This work was funded by DoD CERTIP office. That's a Strategic Environmental Research and Development program. And this topic area is very broad, actually. It's concerned with any improvements that we can make in decreasing jet engine noise. So jet engine noise is an environmental hazard, noise pollution for people that live close to military installations. It's also a flight line personnel hazard, right? Extended exposure to these loud volume levels is very dangerous. The aspect that we tackled actually is that this community in general is lacking in experimental techniques to give you measured values that correlate the plume output to the noise production.